This is part 4 of the course in reinforced concrete beams, and it's the first course to explain ultimate limit state of a beam. This lecture deals with the basic assumptions for the ultimate limit state design, and it gives an overview of the different domains. We will look at elements and at the units that we are going to use for the elements. During the course, we will not always specify the units because we are assuming that the units are fixed. For a bending moment, the units are always kilonewton meter. For shear force, it will always be kilonewton. And the unit of length will be millimeter. And a force can be in kilonewton or in uniform distributed load, it will be kilonewton per meter. The main principle is simple. The resisting bending moment must always be bigger than the acting bending moment. Resisting bending moment is indicated with MRD. So during the course, if MRD is written down, then you know this is the design value, the D, the design value of the resisting bending moment. MED is the acting bending moment. It is the design value of the acting bending moment. Sometimes we will use MD. This is the design value of the bending moment at the point when MED is equal to MRD. So MED means both. We do not apply any sign convention in this course unless it is absolutely necessary to avoid confusion. The sign convention is replaced by action must be equal to reaction. Now let's see the different load types. If you have simple bending, then you have MED, the bending moment, and the reinforcement in the tension zone. So this is single reinforcement, simple bending. Then only MED and AS1 is coming forward. If we talk about double reinforced simple bending, then you have MED and you have, of course, tension reinforcement in tension zone and the reinforcement in the least tension zone. Then you have eccentric bending. It means that you have a bending moment and a normal force. It can be a normal force or a tension. And the reinforcement in the tension zone. This is single reinforcement eccentric bending. You can of course also have double reinforcement in eccentric bending. Then we can have biaxial bending. It means that you have bending according to the x-axis and the y-axis at the same time, and it can be single reinforced or double reinforced. And at last you can have biaxial eccentric bending, which means that you have a bending moment around the x-axis, the y-axis, and an actual force, and it can be single or double reinforced. The biaxial bending we will not consider in this course. We only will tackle simple bending and eccentric bending in single and double reinforcement. Now let's concentrate on the assumptions for the ULS. What kind of assumptions are we going to make to calculate the reinforcement of beams in ULS? First one, plane sections remains plane before and after loading. There is a perfect adhesion between the reinforcement and the concrete. So the reinforcement does not slip in the concrete. It stays on place. The tensile strength of concrete is ignored in ULS. The stress in the concrete in compression follows the parabola rectangle diagram. The stress in the reinforcing steel is derived from a bilinear stress-strain diagram with an horizontal branch. The concrete strain in the design relationship is smaller than epsilon CO2, which is 3.5 per mil. The actual compression strain is smaller than 2 per mil. And the strain in the reinforcement is smaller than epsilon UD, but in this course we will adopt the value of the Belgium annex, and we will adopt 10 per mil. So we will adopt that the strain in the reinforcement is not bigger than 10 per mil. Let's see what's happening in a section. If you have a section, rectangular section, and you have tension reinforcement in it, then you have as a parameter the geometry, the height, the width, the point of gravity of the reinforcement, the tension reinforcement, in principle also the point of gravity of the compression reinforcement. But most of the time D1 equals to D2. So we will leave D2 for the moment out. So we have the height, the width, the distance of the center width of the reinforcement, and then compression and tension reinforcement. That's what your geometry is concerned. Now we go to the strain. In the strain, we know that a plane before loading stays a plane after loading. So we only have two unknowns here, which is the strain in the concrete and the strain in the reinforcement. Then we go from strain to stresses. You have the stress in the concrete and the stress in the steel. And after stresses, you can transform to the force in the steel and the compressive force in the concrete. And this must make an equilibrium with the bending moment, acting bending moment, and acting normal force. Now, if you look at this whole picture, then you will see that we have 13 unknowns, but we only have 6 equations. You can have a rotational equilibrium, transversal equilibrium. You have an equation which gives you the relation between strain and stress, and you have a relation which is integration of stress and forces. So you only have 6 equations, but we have 13 unknowns. What does that mean? It means that the engineer working with reinforced concrete must choose all the other unknowns very wisely. He must choose them in this way that everything gets optimum, that there is no wasting of material or there's no danger for the structure. So it's always a question of making good choices. Now, if we look at a general problem, which is called capacity calculation, it means that the geometry is there and the reinforcement is given. Everything is given. And you want to know this beam, how much force can it take? How much load can it take? Well, then you will see that you need an additional something. You need or the strain or the stresses, because otherwise you cannot calculate the capacity of the section. So if you know the stress or the strain, that's the same because there is a relationship between them. But this means that if you want to calculate the capacity, you must make an assumption about the strain in the steel and the strain in the concrete. So when we are using this, we will use, of course, the maximum strain and the maximum straining in steel and concrete. This is the same. Another problem arises when you have the forces are there, you know the forces, and you want to know what is the dimensions, what are the dimensions of the section. It's a design of a cross section. So you have M and D is given, and you want to know what is now the needed height. And now you will see that you need additional information. You need D1 and D2. You need D1, so it means that you need the concrete cover. You need a reinforcement. And if you got that, you must make an assumption again for the strain, and then you can estimate the needed height and width of the beam. A last problem is the design of reinforcement, which is the most common problem. It is that you got the loads are given, and now you have to calculate the reinforcement. And to do so, you need the section height, the width, the point of gravity of the reinforcement, and again you must make an assumption about the strain in the steel and the concrete. This is important. So if you calculate the needed reinforcement, you must make an assumption about this. Now let's look at the section. Tension reinforcement at the bottom, compression reinforcement at top, or this is the most tension reinforcement, this is the least tension reinforcement, or this is the least reinforcement in compression, and this is the most reinforcement in compression. With their point of gravity DS1 and DS2, we now look at this section, but we turned it around 90 degrees, so that is just the same section, but you see it from the side. You just take one section and you turn it. Now, if you take on the x-axis here the strain of the concrete, and on the other side the strain of the reinforcement, this is in compression and this is tension. That's why it is in the other direction. Action, reaction. This is the strain in the reinforcement. The height indicated here with D from the reinforcement until the most compressed fiber of the section, it's called the effective depth D of the beam, the effective depth D. This is the total depth of the beam. Now we have some three special points. The first one is epsilon UD, which we have taken as 10 per mil in this course. So epsilon UD, it is the ultimate limit strain in the of the design value of the ultimate limit strain of the reinforcement. We also have the ultimate limit strain, the design value of the ultimate limit strain in the concrete, which is for it's 3.5 per mil. For concrete grades smaller than C50. Then we have okay. If you now look at this is a strain plane before loading, and this is the strain plane after loading. Remember, we said it stays as a plane, so it's one straight line. You see, this strain diagram is in fact an optimal diagram because we use the concrete to its maximum capacity and we use the steel to its maximum capacity what strain is concerned. So we use the materials in an optimal way. Not economically, but not necessarily economically, but in strain wise, we use it the best. So that's a very special situation there. If you have centric tension, then you have this line. And between those two, we call this domain 1. You can, starting from this point to the bottom of the section, then we call this domain 2. And then we have domain 3, which epsilon C2 is the ultimate compressive strain with uniform loading. And then this area is area 3. So we have three domains, three special domains, where those two lines come together. That's the third pivot point. So you have this point, and this point are the three special points. The distance where this point is situated is called S. And if you now take this if you calculate where S is, then it's quite simple. It's always the same trick we are doing. This angle alpha 1 and alpha 2 are equal to each other. Alpha 1, or the tangents of alpha 1, is equal to this side epsilon C2 divided by this, which is H minus S, and alpha 2 is equal to the difference of those two strains divided by S. So we know alpha 1 is equal to alpha 2, so we get S. This is the general formula to derive at S. So once epsilon C2 and epsilon CU2 is given, we always know where S is situated. The relationship between the depth of the neutral axis, the effective depth, and the strain in the reinforcement and the strain in concrete by means of similar triangles. This is a general principle in calculating reinforced concrete. You have the plane before loading, the plane after loading, strain in the concrete, strain in the steel, the effective depth, and the depth of the neutral axis. Now, there is always a relationship between them because of similar triangles. We know this angle is equal to this angle. Those two angles are equal. So we can say that when this angle, the tangents of these angles is epsilon c divided by x, epsilon c divided by x, it must be equal to this angle, and the tangents of this angle is epsilon s plus epsilon c divided by d. If you just rearrange it, you have x of d equals this value divided by the sum of the two. So now you see that you can always calculate the depth of the neutral axis if you know the strain of steel and concrete. You will see that in all the domains, at least one of the strains is always given, or it is epsilon c, or it is epsilon s. So again, we have the same diagram with the 3 points. Now we look at all the different domains or the different strain diagrams that can occur for a beam. First one, centric tension. That's the first diagram. Now, if we make it a little bit eccentric, we will arrive at this as a strain diagram. And we continue increasing the bending moment with the same tension force. Then it will incline until we arrive at the ultimate strain in the concrete. So we started with the ultimate strain in the steel, and we applied the bending moment until we have the ultimate strain in the concrete. Then we switch, we take this fixed, and we lower this strain gradually until we arrive at this point, and that's domain 2. Then we take this point as a point, and we turn around this point, and we have area 3. So that's why I call it pivot points. It is where the strain is of the values of the strain are pivoting, the planes are pivoting around that point. This is now general. You can add another axis. This is the strain and this is the stress. We know up till epsilon C2 it's parabolic, after that it's rectangular. And for the steel we do the same. We have the bilinear diagram looking like that. Okay. You can now divide area 1 into 2 zones. 1A, it's from there to there. That means that all the concrete is in tension. And then you have the zone 1B, which is this portion. And then this zone can in fact be subdivided in two other zones, one with the parabolic diagram, one with parabolic and rectangular. Then you have zone 2 can be divided in two separate zones, one like it's indicated here 2A, and then the other zone is 2B. And then you have zone 3. If you now put some figures in it for concrete quality smaller than C5060, you will see that this point is 0.259D, this point there is 3/70th of H, so you have some figures to that. Now, let's assume a situation of strain like it is drawn here at the left border of area 1A. This represents actual tension because this is before loading, and actually you put a force until it's here. So it's actual tension. Now in the zone 1A, 1B and 2A, this zone, it is in fact eccentrically tension because you have the tension that you had and a bending moment that you generally increase. So it's bending moment and tension together, so it's eccentrically tension. This area 1B and 2A, this is simple bending. Those two areas are just simple bending. And then you can have area 1B, 2A, 2B and 3. This is eccentrically compression. This is bending moment and normal force together in different relationships with each other. And at the end, you have centric compression, which is the right border of domain 3. Actual compression. You have learned about the different strain diagrams and domains in the ultimate limit state. See you in the next lecture.